This is the display setup of a multi-channel analyzer. So we have a multi-channel analyzer at the back of this computer, and that's why you'll see we still run it on XP because the channel analyzer here is running on XP. Okay, now this is the detector system at where there is a chamber where you placed your sample or your source, and it should be at the same spot all the time so that you can minimize the uncertainties or any variables during the experiment or any measurement. So because it is emitting photons, you do not want it to go directly to you as you are working on it. So directly after where you place your sample is a crystal detector that is made of sodium iodide that is doped with thallium. At the back here we have photomultiplier tube, if you can see, and this signal will be processed by the photomultiplier tubes and sent to the computer and to analyze by the multi-channel analyzer system. Alright, now we don't have a source, as you've seen that I've opened the chamber just then. We don't have a source, but what do we have at the moment is the background radiation, and the background radiation comes from the radon and the everything that is available in the chamber. So the photons or the ionizing radiation coming from the background will interact with your crystal. So if I go and set it and to check the background for 30 minutes, 30 seconds, you'll be able, I set it to real time, 30 seconds, and I click on go, I'll be able to see the photons interaction or the background radiation interact with the crystal. So as I said earlier in the presentation, the lower energy side of the background radiation has higher intensity, right? And the background radiation diminishes as the energy goes higher. So it does not show energy. What it shows here is the channel number. This is a calibration that can be destroyed, and you should not use that, which I'm not going to destroy now, but this is just a calibration set with one source, so it is not actually correct or it is not actually accurate. Alright, so this is what a 30-second background radiation photons interaction with your sodium iodide crystal. So what's going to happen next? We are going to take a source and observe. So I'll take the, for example, here. Okay. Alright, so we are having cobalt today. Put it in the middle and put it in. So what would you be anticipating from the cobalt? You would see the, how many photoelectric peaks shall we be seeing? 2. Exactly. So let's go and clear all these detector system and say that we want to set the reading to 100 seconds for the sake of this demonstration. Alright, close, and I'll click on go. Can you guess where are the background, where are the content, and where are the 2 photoelectric peaks? Yes? Alright, so this you can just move the roller here so that you can adjust the pointer so that you can analyze the spectrum. So what are you seeing at the moment? Can you explain? Anyone who knows? So what's at the back here? It's your
background.
And this would be?
Content.
And this would be?
Photoelectric.
Which photoelectric? Which photoelectric? This one? 1170. And this would be?
1330.
1330. And now you know all these photoelectric peaks and you know the energy. So we'll wait for 100 seconds and then we will identify the center of the peak and you will get the channel number. And you know the energy, that will be your data 1, and perform the analysis for about 4 to 5 times so that you get a good statistical uncertainties to your observation. So it is up to you in a group to decide if you want to measure this for 60 seconds, for 100 seconds, for 100 to 120. The time of the measurement is up to individual or each group. You guys can decide what is the best, and I would check on how you design your experiment as part of the Viva later. Alright, at 100 seconds it will stop and then we can start to analyze these photoelectric peaks. So I identify this photoelectric peak. This content, we don't know which one coming from which energy, so we cannot say this is the correct energy coming from M, N, and so on. So we always analyze the photoelectric peak. So I identify the beginning of the photoelectric peak. I'll go to ROI and click on mark, and I move the arrow to the right. And I double click on the peak. So this analyzing everything under the photoelectric peak curve. So you get the gross count, which is the count with the background, or the net, which is the one without the background. So if you are observing gross, it should be gross all the way until the end of your experiment. If you're observing net count, it should be net count until the end of your experiment, so that it is consistent. So now, what is the channel number? It will be displayed here as 5.92.24 would be the middle of this peak, the 1170 peak. So you know the peak number or the channel, the middle channel number, and you know the energy. The energy is 1170. So that's your data. And you repeat the measurement for about 5 times, 4 to 5 times. And then you analyze the next peak. Alright, so you'll be analyzing the next peak. Alright, so now you identify where the beginning of the peak. Alright, and then click on ROI. Click on mark, which is already selected, and move the arrow to the right. Alright, and double click on the peak that you are analyzing. Double click. And you'll see the middle channel number would be 670, and the constituent energy would be 1330 keV. So that is the analysis for both cobalt. Now we'll delete everything. Go to ROI and you can clear all and say that we were already to identify the unknown source. So now, Ali, you're in charge. You have to remove the source that you've got here, or you are recording, are you? So one, put your book somewhere. Alright, so now you are to remove this carefully. Place the sauce back into the lead shielded container.
Yes.
Alright, and place the unknown sample in. Place the unknown sample in, the bright color sample, right in the middle. Yes. Alright. Alright. So now you are going to perform the measurement. Okay, clear off all this spectrum. Okay, go to this one below the icon here and click on clear. Alright, go to acquire MCB properties. Say that we want to perform this measurement for 60 seconds. Alright, click on go. So if this sample has been activated through neutron activation, it enables to decay because of its unstable nucleus, and the decay, if it decays through the gamma route, and the gamma photon would be able to interact with your sodium iodide crystal. So you would know this would be the photoelectric peak of the unknown sample, and you would analyze, but you don't know the energy because it is an unknown. But from the channel number, that you can use the calibration curve to identify the energy, and you go back to your radionuclide database and check with that energy what sort of element the unknown sample is. Got it? Alright. Alright, now Selwan, you are going to analyze this page. So how do you do it?
Right up. Okay.
You identify where is the beginning first. Where is the beginning? Alright.
Yes.
And click on ROI. Click on mark.
Right.
Alright.
User. Okay.
Alright. Then,
Center.
Double click.
Double click. Yes.
okay. Can you identify what you are seeing here? The count. This is the count, the number of count or the interaction per second, and the middle channel number. You have to collect these and you have to perform this experiment for at least 5 times, and you have to continue the experiment with an interval time to check on the half-life of this unknown sample. Okay? You perform the calibration curve with americium, with cesium, and with
Cobalt.
cobalt. So you have plot your calibration curve on Excel. Take another source that is barium with a known energy and place the barium into the chamber and check the channel number for the barium and use your calibration curve and test if the calibration curve is correct. Okay? Alright, any questions so far? In terms of time, you have to design the experiment in a group and check with each other how do you design the experiment and what is the time interval, for how many seconds do you perform your measurements, and for how many number of times you repeat the measurement. Any other questions? No? Okay, I'll leave you guys to it and then you can perform your experiment.